Greetings. Welcome to my talk. I'm John Claerbout. My talk is Automatic Default for Hyperbolic Soft Clip. I like this talk and it's really fun and I'm going to tell you why. Uh, I'm going to promise you two things. I'm going to promise you an everyday benefit of improved seismic data display. And I'm also going to show you a totally wild idea, a conceptual idea that might influence many kinds of data processing and data analysis, image analysis. Okay, so let's get started. We'll start by having some gained residuals. Okay, here's some residuals, theoretical minus observed data. We will gain the residuals, and that will define us a new variable. Ordinarily, people don't bother with this because ordinarily people are using norms, the L1 norm, L2 norm, and then a scaling factor in a norm doesn't make any difference. But we'll be using the hyperbolic penalty function, and it makes a big difference. And it's very interesting because it leads us off in a new direction. Okay, so here's a familiar hyperbola, and we're going to take this scaled residual and we're going to plug it in where the x-axis is on the hyperbola. And what do we got now? We got a lot of things going on now. We're going to take the gain, and we're going to take the gain and put it in as the depth axis on the hyperbolas, and we're going to take the travel time, and that's going to be the penalty. Okay, so here's the picture. You pick whichever gain function you like, and if your data residuals are down in this area, if you choose this really high, of course, they'll all be down in this area, and this is parabolic in this area, and so it's like least squares. Normally in least squares, people plot their parabolas looking like going through the origin here. But it doesn't really make any difference where the origin is because it's the gradient that tells you where to go, and you're just following the gradient and you're setting the gradient equal to 0. All of these curves have the same asymptote, okay? And so let's have a look at more details. Okay, here's our hyperbola family of penalties, and here is the gradient. And the gradient is something I'm going to call the soft clip because it's like a clipping function. If g was really big, this thing would be turned into the signum function. Okay, so when we're up in the signum function area, things behave like the L1 norm, and when we're smaller, they behave like the L2 norm. So choosing the numerical value of g is like saying, where do you want to sit between L1 and L2? Okay, so I'm going to make you these two promises. One is to improve the seismic data display, and that's what we're going to do first. This talk began with this slide. I had this data set, which classic data set, which this is gained it by t squared, and I wanted to see what would happen if I just took this data and I put it through the soft clip function. And I got this picture here. And I played with this picture quite a while because it was in my book and I wanted it to look really nice. The most obvious nice thing is that there's an event here, which you can see it now, and there's another event here. So in general, you can see some things better after soft clip. Maybe there's some things you can't see as well. I don't know about in here. You're losing some of the sense of gain. And of course, this stuff here, of course, nobody cares about this. You know what this is, just ground rule. So we turn this into a function. Let's call it a sawtooth function. Okay, so I then wanted to show you a more conventional display as well, and then we will talk about choosing that numerical value for gain, which I did subjectively. Here's some pictures I showed you in the book, and it's hard to judge anything from the book. So we're going to look at stuff that looks more like what I see in the lab. So here is the plot of this with variable brightness display, and this is a default at SEP. And we do a hard clip at the 99th percentile, and so that's why these values are red. And now let's do a little soft clip. So you get this picture here for a little soft clip. Well, that's kind of interesting comparison, isn't it? A little soft clip seems like a good thing. How about some more soft clip? Is that better or not? How about that? Is that better or not? Better or not? Better or not? Or have we overdone it now? Okay, now you might say, why am I clipped here? Why is it red? We use red for stuff that's clipped. What's really happened is that the values are still less than 1, but our screen resolution has only 256 values, and so it's gotten up into that top pixel of screen resolution with it. I'd like you to decide, and I'm going to show you these frames several times, and pick a number. Pick which one you like the best. This is 1, 2, 3, 4, 5, 4, 3, 2, 1, 2, 3, 4, 5, 4, 3, 2, 1, 0. Okay, everybody raise some fingers. 5 fingers if you like frame 5, 1 finger if you like frame 1, 3 fingers if you like 3, 2 fingers if you like 2. Raise them up now and let me count. Okay, so now we know what that is. Let's go on. Okay, so now you've picked it subjectively. You've picked your favorite threshold. Now we're going to pick it automatically instead of and we're going to have an analytical formula so we don't have to do this subjective picking every time. That nobody has to pick this parameter. That's the goal. Okay, so remember that most of the data values were actually 0. Look up in here. There's lots of 0 values. Over here, there's lots of 0 values, and so those 0 data values are all going to end out in the middle here, because what is this? This is the soft clip data after amplitude binning. So if your data value is close to 0, you end up near the center. Now, there's some other points. If you looked like frame 5, there was a lot of clipping on frame 5. Here's the negative -1s clipping, and here's the +1s clipping. I think most of us agreed this one was clipped too hard. And this one here was pretty good, but clipped too soft. And what I really liked was frame number 3, and I hope that's what you liked. Well, I don't know. I'd like to know what you liked, if you liked it or not. It seems to say that what we want is uniformity and amplitude. Nothing we could do about this. These are the different gain values. They actually range from this. Turned out this was the 75th percentile, was used as the gain inverse of the 75th percentile. And this was 1/3 of that, and this was 3 times that. Okay, so that was the range for the gains. So now we'll have a little mathematical digression into Jensen inequalities, and I'll show you how to pick out the one with the most equality. I'm calling this one number 3, an analytic way of picking out number 3. And you'll get this answer, and so it'll be wonderful. What do we have here? The basic idea of convexity is here, demonstrated for a function equals x squared. So on the horizontal axis, we have 2 points, A and we have a point B. Now the function axis, we have a squared and we have b squared. And along this line, which connects A and B, we have a slider. And we can slide this thing down to A, or we can slide it all the way up to B. The other way of thinking about it is we can slide it from A squared to B squared. And as we slide this thing along, we're choosing some weighting factors. We're choosing, could be 50-50 if we put it in the middle, but it's actually 1/3, 2/3. So here we have 1/3 A, and here we have 1/3 A squared. Okay, so we can take this value here, this weighted average of A and B, and we can say what happens when we put this into the parabola, the x squared. Well, then it comes out, this is the same blue box, it becomes squared. What's in this blue box becomes squared. Okay, what is the meaning of, what's the use of this? Well, that's what happens next. Here we have the average of a function, the function being x squared, and here we have the function of the average. Tongue twister there, eh? It's just an average for 2 points, A and B, but B, for example, could be also an average of 2 points, C and D. So in general, we can manufacture any weighted average which this property at the average of the function is greater than the function of the average because this point is lower than this point. So now let's let the variable p be a population of x sub I. This guy Jensen came up with the idea that the average of the function minus the function of the average is greater than 0. Another way of saying it is the expectation of the function is greater than the function of the expectation. And you have this inequality, but the inequality would become an equality if A equals B, or if every member of the population were the same. So now what? So if all these p-values are the same, then the Jensen inequality will become 0. So minimizing J tends to make the p-values become equal to one another. So now we know that if we want equality, as what we're looking for, all we have to do is minimize J. So the question now is, what convex function should we be using? Well, we need to avoid excessive sensitivity to very large and to very small values, data point values, residual point values, or whatever, data values. We don't want to do squaring, not the RMS. We don't want to do the harmonic mean, which is the average of the inverses. We don't want to use the geometric mean, which has the average of the logs, because the log could be 0, the function could be 0, then the log would be minus infinity. So we had to find a function which is not excessively sensitive. You'd like it sort of sense all range, everything, or every range, well, whatever. Seems like the log would be the right thing, but then you have the problem of log of 0. We could easily have a bin with nothing in it, and then we'd have the log of. Okay, well, you can get identical inequalities by either of these two methods here. This one was invented by some mathematicians 80 years ago, and this one was invented by me 30 years ago, but they're both identically equivalent. And the one I invented here it kind of fascinated me because it's very much like the L1 norm, just a little bit bigger than the L1 norm, push a little bit towards L2. But they're both going to lead us to the same place. And my analysis took a whole page of a book, and this mathematician's one is clearly much better because I can do it on one slide. So you'll see on one slide the Jensen inequality that emerges out of this convex function. And I should tell you, if you compute the second derivative of this, it'll be 1 over p. So the second derivative blows up at p equals 0, but this function does not blow up at p equals 0. Look, if p is equal to 0, then log p is minus infinity, but don't let that bother you because this has a 0 multiplying it, and this p is much stronger than log p. So if I were to plot this function for you, I haven't plotted it because you don't need a plot. It starts by going down, straight down, with infinite curvature, and it loops around and goes up. And it crosses 0 at p equals 1. Okay, we don't need to know that. Okay, so here we have this function, and we're going to put this in this Jensen inequality. And so first of all, we can take the function and we're going to average it. So this red thing, this shows that this is just the average of p log p. That's what this term is, the average of p log p. And there's some weights here which are equal to 1. And this part here is a little more complicated and a little confusing. The function here has got blue log blue, and blue is, of course, the average of p. Blue box log blue box, average log average. Okay, so there it is. This is the extrinsic function, and this is found by Hardy, Littlewood, and Polya. Figured this out long before I did. And what I actually use is on the next line. If we divide this one by this, divide it out, now we get something which is I call intrinsic. If you minimize the extrinsic, if you minimize this one, you could get all the p's equal to 0. We don't really not trying to encourage that solution, but here it's normalized, so all the p's equal to 0 isn't going to make you automatically minimum. Okay, so I used the weights are 1 over n, and so this is what I did. Parenthetically, back in 1992 in my book, I said, this is my favorite theory that never quite made it into practice, but today it does make it into practice, so I'm happy about that. Okay, so here we have the about right solution, and here is the entropy. I simply evaluated that J value for the 5 plots we've shown. It was kind of subjective, just really where you were on here. Your subjective analysis, some of you might have ended out back here, I don't know. So 5 values is enough. And it's really nice, the conclusion here, it's really nice that the subjective best value, at least my subjective best, was also equal to the analytic best. So that's the thing. Now, this is just an aside. Some of you might have thought, hey, can't we minimize the horizontal derivative on this thing? And maybe you could minimize the horizontal derivative, I don't know. But you'd have a different type of solution. The final solution here is not rough, but it could be rough. Asking each point to equal the population is not the same thing as asking each to equal its neighbor. Okay, that's just an aside. So now I made you 2 promises, and let's have a look at the second promise, wild conceptual innovation for fitting. Okay, so let's consider a signal where there's large amplitudes and they have one spectrum, and on this signal, from time to time, there's small amplitudes and they have another spectrum. Could that happen? Think about that. Well, what if the spectrum is 3D? Can that happen? Sure, you could have ground roll cutting across reflectors, 2 different omega spectra, 2 different dip spectra. Okay, so that's an interesting case. So a common special case is when we want to ignore large amplitudes. Okay, so here's the big idea. By examining the soft clip gradient as if we were going to plot it, we can find the numerical value of G by using the Jensen inequality. That value of G has put us on the boundary between the L1 and L2 zones. Wow, that's nice. We used to do that subjectively. Now that value of G also belongs in the optimization criteria. In other words, it not only comes about with the gradient, scaling the gradient, getting the right place there, it also comes about in choosing the step length. How far do you want to go? So that's amazing because it says the residual itself is telling us what we want to optimize. So that's the big idea. Wow, we guys used to have to pick that out on our own a priori. Okay, anyway, sorry to say this has not been tried. Hope some students try it, or if they don't try it, I hope you try it. Okay, thank you. Thanks for coming.